Well, welcome back from lunch, guys. My name is Don Barnettson. I'm responsible for our cable products here at Credo, and I am here to talk to you about 800 gigabit and what we believe is the end of the road for DACs, passive copper cables. So let's start with the premise here. So the premise is that 800 gig DACs can be made to work. It's not impossible to make them work, but they're as thick as a garden hose. I don't know if you've actually handled 800 gig DACs. They're as thick and nearly as rigid as a fully plumbed garden hose. They're going to make the switches that they talk to more expensive. So you're not going to be able to support DACs for free anymore the way you could in previous generations. A switch that supports DACs will cost significantly more than a switch that only supports active pluggables. And they're not going to solve any real world rack scale problems because they're too big and too heavy and too difficult to use. So I broadly call this the DAC tax, and it becomes unaffordable at 800 gig, making them truly a dead end. But let me show you how we get here. So if we look at a quick history of connectivity, on the left-hand side we have a simplified data center. We started out a long time ago with the 1 gigabit generation. Everything inside the data center was connected together using passive copper. We didn't call them DACs at the time, but they were passive copper, RJ45, Cat5, Cat6 cables, or DACs, etc. Those cables that go 100 meters, and those cables are about 5 millimeters in diameter. We're all familiar with Cat5 cables. 100% of the ports in that data center supported DAC, and indeed 100% of them were plugged with DAC. As we got to the 10 gigabit generation, which combined together, 4 of those lanes makes a 40 gig connectivity, now passive copper only goes 10 meters. And so we can't do everything in the data center, but we can certainly do everything in the compute rack, and we can do between the compute rack and the leaf node. So the volume of those cables actually got a little bit smaller, which is interesting. 100% of the ports still supported DAC, but now only about 70% of those ports were actually plugged with DAC. The rest were plugged with optical. If you want to get from a leaf node to a spine node or to a routing layer, you'd have to do it with optical because the distance was more than 10 meters. As we move up to the 28 gig generation, the generation that we're just kind of wrapping up right now, we've shrunk it down to 5 meters, and the cables have started to get a little bit bigger. And so the 30 gauge cables are about 1.5 times the volume of that Cat5 cable, but our reach has come down to the point where effectively we're only able to do passive copper inside of a rack today. There's some narrow cases where you can do rack to rack, but you can't do more than just a couple racks over at 5 meters. So now, although 100% of the ports support DAC, only about half of them are actually plugged with DAC. And as we enter the 56 gigabit generation, it gets harder now. So you can see now our maximum reach is cut to 3 meters, and now the cables are really starting to get fat. So we have a cable now that takes 3 times as much volume as it used to. Still 100% of the ports support DAC, but now we're limited even to many use cases in rack simply can't support this today. And so you're starting to see AECs push DACs out of some of those high density use cases. Let me show you what those look like. So if we have an OCP Olympus rack in this case, all of the connectivity needs to fit in some pretty narrow troughs in the front part of that rack. You can come to our booth and take a look. But that trough is only about 130 millimeters or say 5 inches by 1 inch deep. And you have to push all of that cabling in. So in the 1 gigabit generation, you could put 50 DACs in there. And 10 gig, even more. But as you get towards 28 and 56 gig, you can only put about 18 DACs in that space. But the rack scale, in some cases we're seeing up to 72 servers per rack. There's simply not enough space to put that cabling in, let alone the other challenges. As we head to the 112 gigabit generation, which is what's going to come next year, the maximum IEEE reach on a DAC is now 2 meters. But in order to achieve that, we've gone to a 25 gauge cable, which is now 5 times as much volume. So we're doubled up the volume of this thing again. And so the question is, does this solve any real world problems? In addition, it used to be that you get DAC support for free at the switch level. And on 112 gig, you'll see that that's no longer the case. So what do I mean when I say that? So three elements. If you look at serdes power, from the 1 gig to the 56 gig generation, it didn't really cost you more power to support passive copper, to put an LR serdes versus a chip to module and MR serdes in. Plus or minus about 20%. Credo makes lots of different serdes. At the 112 gig generation, an LR serdes consumes twice as much power as a chip to module serdes. And so in that space, if you're going to build a switch that supports DACs, your serdes power is going to double. And what that means for a 25.6T switch is how much, is about 15% more power in this space. On the cost side, if you want to support DACs, you have a very limited host budget. So the CR host budget's been about 7 dB to get from the switch SoC out to the edge for a very long time. That requires a Megtron 8 class dielectric and about 50% flyover cables in this world. Those flyover cables in that dielectric are really, really expensive. They add about 20% cost to that switch, so that becomes a real challenge. In addition, on the complexity side, chip-to-module and VSR ports are able to do it with fixed parameters, where if you're going to do an analog medium like DACs, you have to go into an auto-negotiation link training structure. A secret in the industry is ANLT doesn't really interoperate very well at 56 gig today, let alone at 112 gig. And we've got this structure where we've got these vertical switch makers who are accumulating all of the assets, and they're not really that interested necessarily in making interoperability work at all. So that burden then falls to whoever's trying to put this system together. CR switches are going to be late to market. And so in that space, at 800 gig, there's going to be switches that only support active pluggables, VSR only switch. Those switches are going to be 20% less expensive, and they're going to have about 20% less SoC power. If you have one of those switches and you have a DAC switch that costs more and burns more power, if you're competing for a socket that only needs active pluggables, which switch are you going to choose? Let me show you what that looks like. So if you come to our booth, you can see what a hyperscaler rack might look like in this space. And so this is a spine rack from a major hyperscaler that has 32 1U switches built together into a 400 terabit switch rack. If you build it with DACs, you end up with what you see above me here, which is, frankly, it's kind of a piece of shit. There's absolutely no way to take this to production. There's 150 pounds of cable hanging off the front that sticks 1.5 feet off the front of the server. If you compare that to what you see in an active electrical cable, we're able to go to a 32 gauge, something that's effectively the same size as a Cat6e cable. So we're able to take that and shrink the volume of that cable down by about 75%, and we're able to extend copper for 2 or 3 more generations, to the 1.6T generation, perhaps even beyond that. And we can do that with an active cable, which only requires a chip-to-module interface. So you can simplify the switch design, you can get rid of the flyover cables, you can go with a much lower cost dielectric, and you end up with a solution that is much, much more scalable, much lower risk, and much more viable. So the point here is, at 112 gig, it's certainly possible to make DACs work, but they don't solve real world problems because they put a tremendous burden on the switches, the DAC tax that I talked about, from a power, a cost, and a complexity standpoint. And then the real world use cases for these require you to put DACs at such density that there's simply no way to route them and solve these problems. So in the end, what's the point? Why are we doing this? And I think the clear answer is we won't. There will be lots of demonstrations of 800 gig DACs, but the real world production cases will be limited or non-existent at all. So I would encourage you to come take a look at the Credo booth, which is just over there. It has those racks in it. Or if you go all the way to the Experience Center, we have a huge Jericho 2 Ramon setup. I would love your feedback on that. And with that, I'm happy to take any questions you guys might have. Thank you so much.